we are going to look at vector functions, which are functions whose values are vectors. So, well, the definition is a vector function is a function whose domain is a set of real numbers and whose range is a set of vectors. So here, vector r of t is a vector with 3 components and 1 input. Okay, so it maps R to R3 as a vector. So here, when we write R as 3 components, f of t, g of t, h of t, each of them is a real valued function, and they are called component functions because they are the components of the vector. And then, if again our vector R has components f, g, and h, then we can take limit of the function by taking the limit on each component. Again, assuming the limit of the component exists. Then we can talk about a vector is continuous. A vector is continuous if you take the limit, you reach the point. Same idea as real functions. Now, if f, g, and h are the 3 components are continuous real valued functions in an interval, which means your t goes from t is defined somewhere, then the set C of all the points x, y, z, well, pretty much the components, put them together as the terminal point if you put them in the standard position. You look at how the x, y, z goes. Each t will give you 1 point in the space, and if the function is continuous, if the vector function is continuous, then the movement of the point will be also continuous, which means when your t changes in its domain, all the points it creates will somehow be connected, will also move through the R3 space, and that is called a space curve, where since you express the curve by expressing the components in t, so t is the parameter. Okay, so here the graph, the picture here is showing that pick a t value, it will give you 1 point. Pick another p value, it will give another point. If it is continuous, which means when your t gets closer to a particular value, the vectors also get closer and closer to this particular value. The output of this continuous value. So that makes when your t moves, the vector r moves sort of also connectedly, continuously. That's what this picture is about. When you change t, the curve, each t give you a point, and when they move, since the vector function is continuous, it can't jump this way. It will just goes along one smooth, well, maybe not smooth, but just one path, connected path. Now let's see an example. Describe the curve defined by RT has the components 1 plus t, 2 plus 5t, and negative 1 plus 6t. Actually, we studied this before, right? In the previous section, what we are having is we are having a line with a base point, 1, 2, negative 1, and this line parallel to, well, the vector, the coefficients of t creates the vector, which is the direction of this line 156. Okay, so you are having a point, and then you have the line parallel to this vector 156 through point. Through point 1, 2, -1. Okay, you need to observe how the components are. But this one is easy. We have done this. Next one is, well, a little bit tricky. Describe the curve defined by RT is cosine t, then sine t, then t. So here, x coordinate is cosine t, y coordinate is sine t, and then z is just t. First, if you observe, what happens is x and y are sort of connected more because they're both trig functions, and when you do x squared plus y squared, you will have cosine squared plus sine squared, and that is Pythagoras theorem, well, the trigonometry version, to give you 1. Now let's explore some points. Since we are doing sine and cosine, we'll pick multiples of pi over 2. When t equals 0, you are having 1, 0, 0. And when you have pi over 2, cosine pi over 2 will be 0, but sine pi over 2 will be 1, 0. Then if you keep going, pi will give you -1, 0, 0, since cosine pi is -1. And then next one, 3 pi over 2, you will have 0, -1, 0. Then finally, t equals 2 pi, you will, what am I doing? My t coordinates changes. So, I'm supposed to have pi over 2 here, a pi here, 3 pi over 2 here, and then for t equals 2, we have 1, 0, and 2 pi. So what happens is that your x and y coordinates are on this circle x squared plus y squared equals 1, but the z coordinate, the z components just get higher and higher. So actually the curve looks like this. 1 and 1, so you have a cylinder like this. Then t equals 1, 0, 0 is here, then t equals pi over 2 will get 0, 1, and a little bit above. Then -1, 0, and the pi, so it's somewhere like here. Then we go back to 0, -1, then -3/2. This probably is even a little bit lower on this side. And then finally you go back to the 2 pi. So the curve looks like this in the back. Okay, then it goes up again like this. And the 1, 0, 2 pi, I can't really, it shouldn't be there. It should be much higher. But anyway, you get the idea. This is a curve that, on one hand, if you look at the xy projection, it's just like, well, if you do xy this way, it just goes this like forever, but meanwhile it's going up, and this is called a helix that spiral upward. Okay, it goes upward around the cylinder. Well, the cylinder is, it doesn't really matter what z is, but we need x squared plus y squared equals 1. So that's what the shape really is. It's a helix spirals upward around the cylinder. You need to say upward because as t grows, it goes this way. So the order matters. Well, since our vector is a function now, we can have the derivative and the integral defined. Actually, the way we define it is pretty much if you differentiate a vector, you are differentiating every coordinate. Okay, and actually what you will get is another vector. If you differentiate a vector function, you get another vector, which is called the tangent vector. So it's still the tangent vector. Now, for tangent vector, actually, what matters more is the direction, because the tangent vector describes the direction of how the curve goes. That's why sometimes we want to get rid of the side of the magnitude and only focus on the direction. That's where we get the unit tangent vector, which is t. We denote by capital T. T is, well, the tangent vector, which is r prime, the derivative of r, taking away its absolute value, its magnitude. So it's r prime over the absolute value of r prime. Now let's see actually quite easy example. We want to, we have this curve. R is, on x component is 1 plus t to the third power, y component is t, e negative t, then the z component is sine 2t. Then if you are going to find this derivative, it's just the differentiation on each coordinate. So 1 plus 3t give me 3t squared, that's my I, plus the y component I'm having 1 times e negative t plus t times e negative t times negative 1. And that will work out plus sine differentiate give me cosine, but 2t also give me 2. Sorry, that's j and that's k. So write it a little bit nicer, 3t squared I plus e negative t minus t e negative t, that's my j, plus 2 cosine 2t, that's my k. Okay, so you differentiate each of the components. Now the second question is to find the unit tangent vector at the point where t equals 0. Actually, when t equals 0, if you plug in, you will have 1 plus 0, so that point is actually 1, 0, 0 on the curve, but it doesn't matter. We know t equals 0. We have the parameter. That's all we need. And remember that t of t in general, but here t of 0 is derivative over its magnitude at this point. We know that up there we already have r, so r prime evaluated at 0 will be, well, 3 times 0 squared, which is 0, I, plus e0 minus 0 times, well, whatever, e negative, well, still e0, that's j, plus 2 cosine 0 k. So that's 0, we are having j, that's 1, and that's 2, plus 2k. That's our vector. Then taking absolute value will be 1 squared plus 2 squared, which is square root of 5. And that means my t0 is actually j plus 2k over square root of 5, or 1 over square root of 5j plus 2 square root of 5k. Well, by the way, this actually means you also have the 0i before it. Since it's 0 coefficient, we don't write it. So actually, the vector that you're looking at is 0, 1 over radical 5, and 2 over radical 5, if you prefer the vectored form. The last part of this question is to find the parametric equations for the tangent line where t equals 0. Well, t equals 0, we need To find the line, we need a point and we need a direction. The point, when t equals 0, we need to go back to r. r of 0 will be 1i plus 0j plus 0k. So again, it's 1, 0, 0. That's the base point. And we will already know that r prime is j plus 2k, which means 0, 1, 2. Then put them together, we want parametric equation. So x equals the base of x plus coefficient of the vector t, which is just 1, since we are plusing 0t. Then y is the base point, which is 0 plus t. Then z is the 0 plus 2t. So actually that is the equation. X equals 1, y equals t, z equals 2t. Okay, now you can pause the video and try your case. So here we have a lot of nice rule of differentiation on vectors. That's why we define it. In particular, it has very similar rules to our regular function. When you differentiate a sum, it's the sum of the derivatives. When you multiply by a number and then differentiate, you just get the multiplier out. Now, products. It's very different between functions and vectors. In vectors, we have two products, the dot product and cross product. And what happens is when you differentiate, you pretty much have the product rule as in regular function. So the differentiation is between two vectors, or a function and a vector pretty much follow the same rule as product rule. As in you differentiate a product, you differentiate one vector times the other vector. So they are all f prime g plus g prime f. In a sense, you can't, sometimes you can't switch the order. Okay, so it will be f prime g plus f g prime that way. Because for dot product and regular product, it doesn't matter. But when you are doing cross product, you can't switch order. Okay, but again, it is true for all three multiplications. And finally, we even have chain rule. So when you are differentiating a function, vector function, you can do a function composed inside, pre-composed. So the vector taking derivative will be taking the derivative of the outside, which is the u, followed by the derivative of the inside, which will be the f. So again, they are very similar to our regular functions. Last thing, also same to our function. If you are taking integrals, just like the derivative, when you take integrals, you can take integral on each of the component and then put them together. And if you are taking definite integral, you evaluate at the beginning and the end of t. If it's an indefinite integral, you just plus c at the end. So last example here, we are having a vector which is 1 plus 2ti minus t squared j plus sine t k. We want to find the indefinite integral and then the definite integral from 0 to pi. So we need to find its antiderivative first. So the integral will be the integral on each of the coordinate. So dt, that's my I, plus, well, actually minus t squared dt, that's my j, then this time is plus sine t dt, then k. Work each of them out. The first will be t plus 2t will be t squared I minus a third t third. That's j. Sine taking antiderivative will be negative cosine t. That's my k. you are doing indefinite integral, so it will be up to a constant, but a constant in here, as in the vector space, will be a constant with three components or three coordinates. Okay, it's a vector, so three components. That's how you differentiate and take integral term by term or component by component. Now the definite integral, you just plug in the numbers, will be this huge thing I just wrote, t squared I minus a third t third j minus cosine t k, that is evaluated from 0 to pi. And that is when it's, I'm going to do component by component. Actually, that's easier. For pi, I'm having pi plus pi squared minus 0 plus 0. So 0, that's my I. Minus a third pi to the third power minus, again, 0. Then minus, here I'm having cosine pi minus cosine 0. That's my k. Sorry, I lost my j. This is pi plus pi squared I. And this, the second part, the j part, will be negative a third pi to the third power j. And finally, this is cosine pi is pi, cosine 0 is 1, but you are having negative. So, cosine pi is negative 1. So we're having negative 1 taking away 1, which is negative 2. But you are having minus negative 2, and that is positive 2. Vector k. And that is the definite integral. Just like regular functions, when you are taking the indefinite integral, you end up with a function with a function of t. Okay, that's what I meant. A function of t. See, you'll have all these t's in each of the component. But when you are doing a definite integral, you end up with a vector in your space. And here, since our vector r is in 3 dimension, you end up with a constant in the 3-dimensional space, which is r3. So you have the x component or x coordinate, the y component or y coordinate, and z. Okay. All right, that's it for this lecture.